Hello all and welcome back to this course on computer organization. So in the last couple of lectures we looked at the pipeline hazards, specifically at the data hazards, and we solved the problem using two techniques. One is employing the clock bar, the inverted version of the clock for the register file to handle the read immediately after write problem. And then we also looked at the idea of register forwarding, where the data is anyway captured by one of the flip-flops in the pipeline and you don't have to wait for the register to actually get written back before you give that result for the next operation. So therefore it's a bypass path, or register forwarding as we call it, right? Now in this lecture we are going to look at the idea of a control hazard, right? Because in this pipeline, while data goes through in a sequence, and we also solve the problem using register forwarding and also by stalling, by the way, right? So when you have a load word where the memory is going to give you the data an extra cycle later, then you need to actually stall some cycle, right? So however, there is another problem in this pipeline process, because we are prefetching instructions assuming that that's the next instruction that's going to get executed in the processor. While this may be true for a large fraction of the time, it may not be true occasionally, especially when there is a branching or a jumping kind of instruction that kicks in, where the program counter gets written with a new instruction address and you got to go fetch that instruction and continue from there. Of course, in that case, what you have to do is you have to just simply ignore the prefetched instructions and proceed with the new instruction that you have obtained. So that is exactly what we are referring to as control hazards. So therefore, where does this happen? It happens basically in the branch on equal, right? Now, the problem here, right, is when you do a jump and stuff like that, right, it's known that you have to move unconditionally, you have to jump unconditionally. Whereas when you're doing a branch on equal, you're actually checking the contents of a register, two registers. If they are equal, then you're going to branch, otherwise you do not branch. So therefore, the branch on equal is a harder thing to handle, where the branch is not determined until the execute stage of the pipeline finishes, because that's when the ALU gives you that result and sets that zero flag, as we call it, right? So the instructions after the branch are fetched before the branch occurs, right? So the execute is the third stage of the pipeline. That means in two other instructions would have already entered the pipeline when this comparison between the registers are happening for the branch on equal instruction, right? So these two instructions must be flushed if the branch happens, okay? Only if the branch happens. Otherwise, if there is no branching, then you just continue with whatever sequence that has occurred, right? So for example, what is shown here is some sequence of instructions like this: branch on equal S1 S2 comma L1. What is this basically doing? It is going to do comparison of S1 and S2, and then it will branch by calculating a new address provided by the immediate data L1, right? The PC will be updated with that particular value, okay? So what is going to happen if you look at the sequence of these instructions? We know this timing diagram pretty well now. So if you look at it, the instruction memory, from the instruction memory you have fetched the branch on equal. The register decode, or the decode stage, is now going to decode S1 and S2 for you, right? And the contents of S1 and S2 will be read out and given to the ALU to perform a subtraction operation. And that's when the zero flag, that bit will get set at the output of the ALU, right? And then you're going to go to the data memory and register file read back. But now the branch, after the branch on equal, assume that the instruction is subtract S8 T1 S3 or S9 T6 S5, right? These are two R type instructions that you're doing. So basically, while the register file is sort of decoding these branch on equal register values, S1 register addresses, S1 and S2, the subtract instruction is fetched, and then in clock cycle 3 the register file decodes the address T1 and S3. Likewise, in clock cycle 3, the OR address is the OR instruction is fetched, and in the next cycle you are going to decode this T6, S5, and then perform the subtraction and all that. So the point is that in clock cycle 3, what you really have to do, right, is to figure out that, okay, the 0 flag has got set, which means I cannot go ahead and simply execute this subtraction and or this thing. You have to prevent the execution from happening. It's okay, you have prefetched it, you have decoded it, but do not execute it, because then lot of things can change, right? So you have to basically flush these instructions, okay, and instead the new PC, the value that you have calculated, right, basically you need to sort of get it from there, right? So that's what this L1 label is here, right? You're loading the PC with that new label, and then you're executing add S7, S3, S4. So therefore what is going to happen is, after clock cycle 3, in clock cycle 4, you need to flush those two instructions, right? And you got to start from the fetch of the add, okay, because which is sitting in some address 58, hexadecimal 58, right? So the point is, you have to start from the fetch here, because you have no other go. That means the execute for the add can happen only in clock cycle 6. Usually the next instruction was supposed to execute in clock cycle 4 itself, right? If the branch wasn't taken and you are performing subtract and OR, then the execution of subtract would have happened in clock cycle 4, execution of OR would have happened in clock cycle 5, right? Now we are saying you have no choice. You start fetching the new instruction add S7, S3, S4 in clock cycle 4, and then decode in clock cycle 5 and execute in clock cycle 6. So therefore you have no choice but to waste 2 cycles there because of this branch that has been taken in this case, right? Hopefully the branch is going to be taken very occasionally, right? And for when you do a for loop or stuff like that, it's possible to sequence the instructions so that the branch is taken very occasionally, right? And therefore you can avoid this flushing and wasting of cycles in order to improve your performance. Okay, now what is the control hazard flushing logic? Okay, so if the branch is taken in the execute stage, then you need to flush the instructions in the fetch and decode stages. Basically you have to flush them. We'll see what flushing means. We already used flushing in the earlier idea of stalling and stuff like that, but we'll see what that actually means now, okay? So you do this by clearing the decode and execute pipeline registers using flush D and flush E, okay? So if you look at this, what you are saying is flush D is equal to PC source E, okay? So what are these signals? Let's go back and we can look at this out here. We are looking at the PC source E, which is essentially the output out here, the output of that AND OR gate. So what is it? You are basically the output, that AND OR gate is being controlled by the 0 flag of the ALU, okay? So you are looking for 0E, okay, and the control logic has said it's a branch or it's a jump, okay? So you're just saying that PC source E is going to tell you, look, the PC source is not just PC plus 4 now, it needs to be something else, okay? And therefore you're going to go ahead and appropriately set the input to this particular multiplexer, right, which is going to choose between PC plus 4, right, or the new PC target that is coming out of this particular guy here, okay? That's what the PC source E signal is doing. And therefore in my logic, all we are saying is, if you want to flush in the decode stage, right, then you say PC source E, because if PC source E has gone high, it means the branch is being taken, and in that case you just flush the D, right, and then you flush the E. What is the flush in the execute stage? It is basically either the PC source E has gone high, right, or you want to stall because of the load word. You remember in the load word we had to stall a cycle, so therefore you couldn't do anything, you just had to stall it, and that's why you do this flush E. Okay, so basically that's what is showing here. So the hazard unit is going to implement this particular logic as explained here, and it is controlling. Now note that the flush E, the flush signals, you know, in any stage are simply controlling the clear of the flip-flop. That means all that you will do is to make the output of the flip-flop equal to 0. Okay, and on the other hand, the stall is controlling the enable, right? Of course it's going inverted, but effectively what we are trying to say is that you will stall something. Okay, here also you see this, which is controlling the program counters register, right, the flip-flop, right? So what is the implementation of this flip-flop? You know, there is a clear, there is a reset and all that. So basically what we are trying to do now is, you remember our our flip-flop with an enable, right? So if you look at this, I will give this kind of a D Q clock, right, and this is my actual D input. This is going to come out like this out here, and you get Q, okay, and therefore you have enable, right? So this is one way to implement the enable signal for the flip-flop, D flip-flop, okay, or the register, whatever it is, right? So when enable equal to 1, the new data will get written into that flip-flop and it will come out of the other side. Otherwise it is the previous data which will just get held like that, right? So that is one way to do the enable, do the enable control, right? On the other hand, now what I want to do is, I also want to implement a flip-flop with a clear. So what is the clear signal? The clear signal can be implemented again, it can be a synchronous clear or an asynchronous clear. Synchronous usually is better, right? And therefore you could do this again in multiple ways. You could just put an AND gate here, okay, you give a D and then you do a clear. So you want a clear here, so which means I will say clear bar. So if clear is equal to 1, right, then you want to basically make the output of the flip-flop equal to 0, right? Now the problem with this implementation is the enable has to also be high at this point, and therefore at that point if you do a clear, then it will go through, right? And therefore this is a very valid implementation of a flip-flop with a clear signal, right? So now let's get back to this unit, the flush and stall unit. The flush signal is controlling the clear, right? So you are going to make it, you want to clear when flush goes high, you are going to clear it and therefore make the output of that flip-flop go to 0, right? On the other hand, the stall is controlling the enable. So the stall bar is actually enable. So when stall goes high, enable will go low, and therefore it will not allow the new data to go through, it will just hold the previous data, right? So that's one way to implement this whole flushing and stalling unit at a flip-flop level, right? So with that, what we have basically been able to do now is to simply implement our hazard unit, right? And so if you look at this, the RISC-V with the hazard unit, all the signals are basically shown here. right? And they control the forwarding, they control the branch on equal and all that, right? So in summary, the hazard unit implements the following logic. Okay, it takes care of data hazards, okay, which controls the source A of the ALU. I mean, what we have shown here is only for source A. Similar thing has to be done for source B also. Okay, so if the source RS1 register in the execute unit is equal to the destination register of the data memory, this thing, right, and reg write M is equal to 1, of course, and the RS1 in the execute unit is not equal to 0, that is, you are not trying to write back to 0 register, then forward AE equal to 1 0. Okay, so it is selecting a path so that you are able to forward from the from one of those registers. On the other hand, if RS1E is equal to the destination register in the write back stage, right, and reg write W equal to 1, okay, then, and of course RS1E is not equal to 0, then you are saying forward AE equal to 0 1. Okay, you are selecting the path from the data memory readout path. On the other hand, forward AE is equal to 0 0, where you are not trying to forward, you are just trying to send data in the normal path from the register file itself, right? And of course, the load word stall logic is basically LW stall. RS1D is equal to, in the decode stage, is equal to the R destination, the execute stage, or again RS2D equal to RDE, right? Then you are saying stall F equal to stall D equal to LW stall, right? So basically this is the logic that has to be implemented. For control hazard flushing, you are saying flush D equal to PC source E and flush E equal to LW stall or PC source E.